Hello, everyone. My name is Fabio Niephaus. This is my colleague, Patrick Ziegler. The both of us are working on the GraalVM team within Oracle Labs. And today, we're going to talk about the future of write once, run anywhere, from Java to WebAssembly. So some of you may know that we have a WebAssembly runtime that you can embed in Java. That's not really new. There's other runtimes like Chicory, right, that you can use. We're going to talk about GraalVM at the end a little bit. I want to show you a cool demo, something that we can do with our GraalVM stack. But today, we're really keen and really excited to show you the other project that we've been working on, which is our WebAssembly backend for GraalVM. So we thought we show you a demo, and to be honest, this is a bit crazy. So bear with me, and hopefully, we'll get through the demo. At least I prayed to the demo gods. So what we're trying to do is I'm going to open my Chrome. And this is the Java compiler, Java C, compiled with GraalVM to WebAssembly, running in the browser. And here's a simple hello world written in Java. So I can compile it. I can compile it in the browser, and it compiles just fine. If I put in a typo and I recompile, I get an error message from the compiler. Right? So let's go back and let's compile. And here's a class file. We're going to take a look at that later. But we can also use Java P to disassemble everything that we just compiled. So here you can see, for example, the string that was in there. And this is Java bytecode. Right? So just to make sure that this is not fake, let's replace this and say wasm.io, compile. And now we're going to download this. In my download directory, there's now a new file. Hello Wasm class, which I can run on Java. Right, so this is Java bytecode compiled in the browser. And then I ran it on Java. Hold on, but didn't we say we can compile Java bytecode to WebAssembly? Well, yes, and let's do that. So we have Native Image, our tool for AOT compilation. And I can enable the experimental WebAssembly backend, and I can call it with the same argument that I called Java with. So now I'm kicking off a build with GraalVM. This is using the WebAssembly backend. There's a lot of things going on. But within 6.3 seconds, we now have a WebAssembly module that I can run on Node. Right? OK, cool. And to tell you all about how this works, I'd now like to hand this over to Patrick.
Yes. Thank you, Fabio. This is all built on our GraalVM ahead-of-time compilation technology, right? Native Image. So maybe let's just quickly go over how this works. Usually Java is a just-in-time compiled language, right? At runtime, the compiler dynamically figures out what you want to compile, so on. And GraalVM is kind of more classical compiler like your GCC, right? It takes as an input your applications, your libraries, your standard library, in this case also some GraalVM specific code, takes it all in, compiles them into a native executable. And for Native Image, the way we do this, here in the middle, we do a fixed point iteration on our static analysis. So the way this works is we start at our main entry point, so that's your main method usually, and from there we spread out, we figure out all the methods that this thing calls and that all those things call transitively. We do this in an iteration until we no longer discover anything new. As part of that, we may have to run some Java static initializers, and as part of that, some Java objects may get created. Those are then snapshotted, and in the final image are emitted as something we call the image heap. So that means at runtime, you don't have to reinitialize those objects. They're already there for you. And right, traditionally, native image would then produce a native executable, for example, like for Linux on x86, right? And now where we come in is really just that last part here. We will now generate a Wasm module out of the whole thing. Everything in front here, that's more or less basically the same, of course, with certain modifications, but the core pipeline is unchanged. Just in the backend, we now emit, for each function or for each method, we emit a WebAssembly function and then package everything up into a Wasm module. Right, this, we target the Wasm GC proposal, and currently this is also targeting a JS embedder. So there is a JavaScript binding that's produced with the compilation. You may have already seen this in a demo, right? There's the hello Wasm that you actually run is a JavaScript file. This provides some imports for the Wasm module, downloads it, instantiates it, and so on. Like it provides, for example, the printing functionality, because otherwise, like it's Wasm, it doesn't really do printing by itself. Yeah, already mentioned this. We're targeting the garbage collection proposal and exception handling. This makes like mapping Java to Wasm a lot easier, right? Every Java type is represented as a WebAssembly struct, and exception handling, same story, right? Basically, what maps almost one-to-one to WebAssembly. This helps a lot with just complexity. It helps with code size. Currently, Hello World is around 1 megabyte in size. Seems pretty big. Of course, it is. For a Java program, it's not that big. Also, this is before you even do compression or running Wasm opt. If you do all of that, you get down to like 300 kilobytes easy. Another nice thing that we have here, because we use Wasm GC, we can now share Wasm Java objects with JavaScript, and we can share JavaScript objects with Java. And we have like a nice JavaScript interoperability API that does this. And like in the demo you saw before, like all the buttons, all the interaction, that was all backed by Java code. So every button had an event listener that called Java code that did the actual compilation. And like the API handles conversions of all different types for you. It handles method invokes and so on. There's really a lot you can do if you're targeting a JS embedding. Another thing here is that you basically have the whole Java standard library, the JDK, available to you, right? Java P, Java C, they're all shipped with the JDK. You just have to import them and call into them, and they're available to you. Of course, not everything is working. Things like threading, networking, graphics, that's all things that will just throw an exception right now if you call them. But it's all step by step. Right now, what does work is, for example, file system. Those parts have been appropriately substituted in the JDK. In like an in-memory file system. So you have all the file system stuff available, it's just not persisted anymore. But you can use it. And it's also used in this demo, right? For example, at the beginning, when the app starts up, it first populates the in-memory file system with all the JDK classes it needs. It writes the actual Java file into the file system, where Java C then reads it out again and then places back the class file that it has finished compiling. And finally, we do plan to contribute this to the open source GraalVM Community Edition. But if you want to get your hands on this right now, it is available as a preview build, an early access build of Oracle GraalVM. It's available in EA Build 15 for JDK 25. SDKman does not currently have it, at least last we checked. Let's hope over the weekend this should be in there. It is available from our GitHub page, where we provide these early access builds as well, so you can use it. Hello World also works with earlier versions, but you need version 15 to get like the Java C demo working. You also need binarian. We use that one for assembling the final binary. We just emit the text format, and binarian then takes care of actually producing the WebAssembly module. And the last part, this is more just for reference, right? You use a native image tool like you would for compiling any other Java application, but you now use the --tool /svm-wasm option to turn on this new WebAssembly backend. All right. This is like the rough outline of what this thing actually is, and there's a ton of things I could talk about here, but I just don't really have the time, so I'm going to drill down on just one thing, and this is how we're using the Wasm GC proposal, specifically the type hierarchy it provides for us to map the Java type system, and how we then use this for doing type checks, for doing Java type checks in Wasm GC. Right, on the left here, you have the Java type system, well, the type hierarchy. This is pretty straightforward. Just want a quick refresher on how the arrays are laid out. So there's primitive and object arrays. Primitive arrays are just all objects. And the object arrays have their own little type hierarchy, right? If a class A is a subclass of a class B, the arrays of A will also be a subclass of the arrays of B. So something that Java has. And we'll see now how do we actually map this into the Wasm GC type hierarchy. And we do this more or less by just shoving the whole thing under the struct type. So pretty straightforward. Every Java object has a struct definition, or most of them do at least. Like all regular objects do, right? Number, integer, all regular classes have that. For arrays, the story is slightly different, just because a bit of the quirks of how Java works. One thing we did is we introduced this base array type, which Java does not have. It's very useful in Wasm GC because you can read array length without knowing what the actual array is, which is something you can't really do in Java. In Java, you just let the JVM do this for you, and it does some unsafe magic, and it works. But for Wasm, you can't really do this. You need to be very precise about what you do because everything is supposed to be type safe. Next, the primitive arrays are just the same as they are in Java. And now I think the biggest limitation of this here is the object arrays. We had to represent all object arrays as a single struct definition in Wasm GC because how the Wasm GC type system works, right? You cannot have arrays subtyping each other if the arrays are mutable. So we can't really have the same type hierarchy as Java has for objects, which makes a lot of sense because for Java, this is also not totally sane. In Java, every time you store something in an array, there is a runtime check to make sure that this is actually a valid store, because you could take a number array, cast it to object, and write a string into it, which of course does not make any sense. In Java, this just fails at runtime. Wasm GC will just not allow you to do that at all, which is why all object arrays are just one single thing. And we'll see how this actually then now translates into type checks in the final WebAssembly binary. So let me switch to a terminal here. Let me see here. Yes. So I have just a very small Java program here on the left that does a bunch of type checks, right? A bunch of instance offs against some input object. And on the right here, I have the compiler output of our Wasm backend, right? This is one-to-one mapped to a Wasm function. And if you check here, the first if is very basic. It uses ref_test, which is Wasm GC's built-in subtype checking. Because number is part of that hierarchy and does faithfully represent all those relationships, we can just use Wasm's built-in instructions for this. The second one, which is the check for string, should be the same. In this case, it's a bit different because the compiler figured out, hey, string doesn't have any subtypes. So instead of doing a subtype check, I can do a type equality check. Now, Wasm does not have type equality checks, unfortunately, so which is why we need to fall back to our own implementation of this, which uses the metadata that Java already has about types, right? The class object, which encodes this kind of information. The next is going to be the object array. This looks exactly the same, right? Object arrays can be represented as those structs. So we just do a regular ref test again against this struct, which is, in this case, of course, represents all object arrays, but it is also enough to just check for object array specifically, since this is a subtype check. This stops working once you get into type checking against subtypes of object array, right? So if you want to know if something is a number array, you can't really do that in WebAssembly, because at runtime, right, the type of reference you have, it's the same for all object arrays, so you can't really do it type check there. So we also fall back to our internal type checking algorithm for that. I'm not going to get into how this works. This is it's pretty complicated, so it's I think just going to skip over that. But we have all that information available in our internal metadata about which classes are available. All right. Now. All right. Yes. So, I mean, you've seen the demo about Java C, right? And it's a pretty cool demo. But like, why is this useful to you? Why would you want to like compile Java C all over the place and put it in your on your websites? Usually you don't, right? But this is a general use case, right? Turning command line interfaces into web UIs with the same underlying code. So an example here is we have something called the Graal Development Kit, which is a Micronaut-based framework, Micronaut-based microservice framework. And it has a command line interface, which you give it certain configuration, right? Some command line flags, and it will then create a project template for you based on those flags. And now with this backend, right, you can take the same underlying Java code, write some Java glue code around this that then that exposes the right functionality, build some nice UI in the web, right? Of course, this you have to do by hand. This is not something Java can do for you, obviously. But you map all those configurations. You map to nice selectors or radio boxes, whatever. And then when you press the button Generate Project, you just call into the Java code. The Java code creates a whole project for you, gives you back a zip file, and you let your users download that. The underlying code is the same, right? Usually, you would have to rewrite the whole logic about how the project is composed. You have to rewrite the logic, usually. But with this, you can just take the existing Java code, compile to WebAssembly, put it on the client side, and don't really have to duplicate any work. You can just reuse the same thing pretty easily. And with that, that's the end of my part. I'm giving back to Fabio.
Thank you, Patrick. So this was the WebAssembly backend for GraalVM, and now we'd like to talk a little bit more about GraalWasm, because we're at the Wasm I/O conference. So in case you didn't know, GraalVM provides different languages. We call them Graal languages. GraalWasm is just one of them, and it's ready for production. It actually implements several different Wasm features, as you can see on the WebAssembly website. Here's a screenshot of that. And we primarily use that for embedding Wasm code in Java applications. However, you can also download GraalWasm on its own as a standalone distribution if you want to run it, for example, instead of Wasm time or some other Wasm runtime. You can do that too. Even use our tooling, which you'll see in just a bit. We also have a JavaScript runtime, which is called GraalJS. And GraalJS implements the WebAssembly ES module integration. So that means you can use JavaScript bindings to facilitate high-level communication between Java and WebAssembly, right? So whatever like Wasm bindgen spits out, you can just use that to interface from Java to JavaScript, and then from JavaScript to Wasm. And lastly, in the following update, hopefully we can finish our work on the SIMD proposal, but we also have some exciting, cool updates on debugging with Draft. And because debugging on the server side, debugging WebAssembly on the server side is all the rage right now, and we saw a great talk by Microsoft today, we figured we sneak in a little debugging demo as well. OK, so here's VS Code. And this is a Spring Boot application. The Spring Boot application implements an endpoint called photo, and then it takes an effect name. I can run this on my computer. And this is an image that you would get from the service. This is actually already applying a filter called flip H, but we can also apply flip V. And then we flip the image vertically. Right, so this is Photon, a photo image processing library written in Rust, compiled to WebAssembly. And we're using our JavaScript and GraalWasm runtimes to embed all of this in a Spring Boot application. Right, so that's kind of crazy. But what if something is wrong with this pixel? Right? Like, how would you debug this? We are in a Spring Boot application that has embedded Wasm code, and we're talking through JavaScript to the Wasm module, right? So let me kill the process real quick, and let me start a different configuration with the dep profile. So all of our languages are implemented in the Truffle framework, and the Truffle framework provides tool support, one of which is the debug adapter protocol. And the debug adapter protocol is a first-class citizen in VS Code. So now I can go here, and I can start a debugger session. And now I'm connected to the process. You may have noticed the application hasn't actually gone up yet. We're still booting, and now we are evaluating something that looks like JavaScript. Well, I can show you why, because the thing that initializes the application in the pool, this just happens to be the first that we're evaluating in JavaScript. So this happens right before we actually load the photon module. Right? So that's the very first request that we get. So now let's see in the debugger, take a look at the loaded script section. When I now resume, the application comes up. Here we go. Okay, and in the loaded script section, we have a bunch of files. Well, we have lots of files in the cargo directory, which happen to be the dependencies of Photon. And we have Photon itself, which I built on my machine with dwarf info on, right? And we have the binding. So here's the Wasm bindgen generated code that glues the JavaScript binding together with the WebAssembly code. Here's the WebAssembly module, and here's the JavaScript binding. So we've been talking about flipv, which happens to be in here. And conveniently, I have set a breakpoint already. Right? So let me fire up the request again. And we are in the debugging session. So what's really cool now is this is running in GraalJS, and the Wasm code runs on GraalWasm, and GraalWasm has also support for our tooling based on dwarf, which means I can step in now, and now I'm looking at some frame, which actually happens to be a generated frame from Wasm bindgen. We can see that here. Right, so let me step in again, and then we see something crazy. This is an effect of the compiler. Well, there's an inline statement, so the compiler has decided to inline this. OK, so far so good. Let's just step in again. OK, another inline. OK, here we go. flipv. Now we are in flipv code, and here's the photon image, right? So we can actually look at the object. So this is the Rust frame running in Wasm, and this is the JavaScript frame. Here we have JavaScript module and a photon image JavaScript object with a pointer. And on the other side, we have a photon image, which is then processed, right? So we can even look at the image. It's some, I don't know, this is Rust, and I'm not so much of a Rust guy, but yeah, we're reading width and height. And now we're creating a new image with width and height, and we iterate through the original image, and then we read every pixel and put it in the flipped image. Right? So here's the pixel that I was talking about in the browser. Unfortunately, in this demo, I can't change the value. I was going to change it to something red and show you the red pixel. But this is work in progress. It hasn't actually been committed to master yet. But we're going to hopefully be able to ship this in September. OK, so now I can step, and we can step through every pixel. But I don't want to bore you too much with this. So I'm just going to resume, and then we can see the browser request is finishing. OK, great. So this is debugging. So yeah, so this is debugging with debug adapter protocol. Obviously, it doesn't just work in VS Code. It works on any IDE that supports debug adapter protocol. We also support the Chrome Inspector protocol, which conveniently is also integrated in IntelliJ, right? So you can even do all of this in IntelliJ. Here's a screenshot of the two IDEs. But what's also really, really cool, I think, is we have more tooling, for example, profilers. And because I thought it's a good idea, I ran the profiler on this thing yesterday. And this is me profiling the application that you just saw with a single request. So this turns out to be the loading part, like loading an image. This is flipv, which apparently is really fast, right? And then converting it back into a byte array that can be sent back over wire is apparently slower here. So, and what we can see here is a Java thread running JavaScript code. Right, JS, there's a little JS right there. The Wasm bindgen is all over the place, right, gluing everything together. And then the Rust code, right? So, and it's just an SVG, and we also integrate other profiling tools. So, yeah, give this a go, try this out, and let us know whether you find this useful. OK, so that was GraalWasm. That's our Graal language for WebAssembly, and that allows you to embed WebAssembly in Java applications, as we've just seen with the Spring Boot application. GraalJS also allows you to reuse JavaScript bindings and facilitate high-level communication between Java and WebAssembly. We're watching out for the component model, and hopefully one day we can do direct interop between Java and WebAssembly, but we're not there yet. But in the first part of this talk, we introduced the WebAssembly backend, and finally we have gone full circle. So GraalVM can now generate Wasm GC for Java applications. The Wasm modules are built with the JDK25 EA builds, and the WebAssembly backend allows you to do high-level interaction between Java and JavaScript. And with that, thank you very much, and we are happy to take any questions. Yep. Oh, I forgot to mention, the Java C demo is, of course, up on the internet. So if you want to try this out on your computer, or if you want to try this out even on your mobile phone, if you fancy building or generating JVM bytecode on your mobile phone for whatever reason, right? Here's a link. The source code is up on GitHub. You can take a look at all builds with GitHub Actions, so you can reproduce what we've just done. And yes, so now we are taking your questions. Thanks. Oh.
Really awesome presentation today. I'm super excited about this. I have two questions. One, it's about the support of the reflection API, if you fully support it or not, or what's the caveats that might
so
exist right now?
the reflection support is basically on the same level as what Native Image has, and their reflection is basically turned off by default, but if you need it, you can select classes or entire packages you need reflection for. If you do like class.forName, it will detect it for you, stuff like that. So you can get reflection metadata into the image, but if you don't need it, you don't have it.
OK, just to not pay the cost, basically.
Exactly. Yes.
And the other question is regarding WASI or WASIX. So do you plan to have any support for it?
Yes. I mean, we're right now targeting a JavaScript embedder. We have our own custom bindings between those. But yes, I mean, especially after like being here at this conference, it is clear that like the component model is the future, and it's something we do need to support in combination with WASI. So it's definitely something I want to work on. Yeah.
Awesome. Thank you.
Here. Yeah, so thank you for that. I'm constantly impressed by what is happening with Graal. I think it's so cool. I want you to continue doing what you're doing. Just a curiosity, I noticed you mentioned that you're targeting WAT and then using binary in to create the binaries. Why?
Because I'm lazy. I just
Okay. Just because it's easier?
Yeah, I mean, like generating the text format is easier, at least for me, I think, than generating the binary format, because I don't need to care about, well, which ID has which number and all that kind of stuff. Of course, it precludes some things, right? It's difficult for us to now generate dwarf debug info because we don't control the assembler. But it's more like, at the time, I'm not going to like spend time doing this if I don't need to. I think at some point we're going to have our own assembler, but for the time being, it's binarian.
We're still around in the coffee break, so feel free to get in touch. And otherwise, thank you again, and enjoy the rest of the conference.